All right, so if I'm going from 0.25 up to like 0.85, then like what's in between that? 0.2 and 0.8. Like 0.5 or so. So I need to be like around 0.5 here, 0.8 here. So I was just trying to think like what seems kind of like a reasonable scale to go up by and choose a nice round number. And then if you end up getting sort of like to here, like you're counting off the squares and you get, sort of at the end of your scale and you're less than halfway, then you always know, oh, I could just half my scale or double my scale, or however you want to think about it. You're always trying to get the data to fit across at least more than half of the axis. If you go to set a scale and like all your data is between here and here, just double the scale, right? And it will go to here, okay? If you choose a scale and your data goes more than halfway, then you're good, okay? And so if I want to go from like 0.25, like could I make each one like 0.01? So like could it go 0.26, 0.27, 0.28, 0.29, 0.3? So like every one of these will be like, so it's like 0.3, 0.35, 0.4, 0.45, 0.5, 0.55, 0.6. 0.65, 0.7, 0.75, 0.8, 0.85. So if that one right there is 0.85, you see how, well, you probably can't see because it's so small, but if you've got really good eyes, or if you've got maybe a good imagination, you can imagine that this goes from 0.25 over to 0.85 here, and it's more than halfway, and I'll capture all of my data, right, which range from this value to like 0.81. So that's a good scale there. So every square on this, and I didn't start at 0, in other words, because I have like, I don't want dead space in my graph where it's like from 0 to 0.25, I'd have to have what, 25 of these squares where there's just nothing. So rather than plotting a true 0, I'm showing I've broken my graph and I'm starting at like, this value, 0.25. So I've got to show that. So 0.25, 0.26, 27, 28, 29. So I'm just going to label some of these, like this one's 0.35, 0.45, 0.25. All right, just kind of filling some of those so that when I go to plot my data, it's a little bit easier to read. Now, it's so worthwhile to, the first data point is, well, you can plot it in any order you want to. I'll probably plot it in the reverse order that we collected it. So my points will go this way. So I'm going to plot 0.25 against 0.980. So my t-squared axis goes from about 1, okay, I'm plotting 0.98, up to about 3.2. So I might, you wouldn't want to say, well, my highest value will be 3.258. That's not a nice round number. You want to be at 3.5, or 3.25, then we might make our data point just above it, but it's better to sort of capture your range of values. And so if I want to break my graph and call maybe this square right here, if I call it 0.75, could I go, so this would be 1, 0.75, 0.8, 0.85, 0.9, 0.951. Let me see if that'll work. So if I call this 0.75, so every square is like 0.05, 0.8859951. I don't know if that's too small of a scale to get me up to 3.5 or whatever. In other words, I said every square is 0.05, which means this would be 1.25, 1.5, 1.75, 2 would be here, 2.25, 2.5, 2.75, 3, 3.25, 3.5. So 3.5 is like exactly halfway, I think. So that's nice. I just sort of half my scale. Except for we're doing it by 5. So half of 5 is 5 halves. And then we're back to like, I want nice, neat, round numbers. So if I made it, so in other words, I said if everyone was 0.025, then instead of getting from here to here, it would take 10 squares to get up to 1. So it'd be, so like 1 would be here. So it's going like 0.75, and then this, instead of going up to 0.8, it's going up to like 0.775, then 0.8. So in other words, I just half the scale. So this would be like 0.8, 0.825, 0.85, 0.875, 0.9, 925, 95, 975, 1, and so on. So between every 10 of these squares, it brings me up a quarter, okay, from 0.75 to 1. So I'm going to go up 5 10 squares, and they're easier, you know, like this is kind of convenient to count by 5s and 10s, like each one of these kind of bigger squares here is 10, right? So half of is 5. So what did I say? I'm going up 10 squares for 0.25, so I go 10 squares, and it's 1.25. I go up 5 10 squares, and it's 1.50, 5 10, 1.75, 5 10, 2.0. Go up 5 10 squares, and 2.25, 5 10 squares, 2.5, 2.75, 3.0, 3.25, 3.50. Don't get much better than that. All right, so you can see how it is a little bit of trial and error, okay? You get a sort of an intuition or a feel for it. You're like, oh, I kind of know I'm going to be about here. If I make that halfway, you know, what seems reasonable? But you see how everything is nice, like every 10 squares, it's gone up by a quarter, right? So every square, and sometimes it's helpful to write it out, like every square here is 0.0025, right? So if it's going up, like I said, 0.75, the very next square would be 0.775. So it's going by 0.025, right, per square. 0.025 per square. This one was like 0.1 per square. Because it went 0.26, 27, 28, 29, 3, and so on. Okay. Let's go ahead and plot some down. The first data point that I'm going to plot is the last one that we collected. So it's 0.25 on the x-axis, and then 0.98. And so if I go to 1 here, but what was every square? So this one was 0.975. And so it's above that square, but not quite touching this one. You want to use a small cross for your data points. And you're sort of saying where those two lines intersect, that's where my data point is. So it looks like a dot because I'm zoomed out. But if you were to zoom in, like if in class you can see in the e-learners, like a small cross. The next one I'm going to plot is 0.316. And so this right here would be 0.3, 0.31, that'd be 0.32. So it's kind of like right in between these two squares. And it's going up 1.279. So this one's going to go up to 1.25. 1.275 would be there. And I'm trying to plot 1.279. So you see how it's like I'm using the nice scale that I've made to let the data just sort of fall where it does. This to be a little bit above that line, because that line right there is 1.275, and I need 1.279. Moving right along here, I got 0.407, so that's 0.4. 0.41 would be this one. So I go to 0.407, and I'm going up to 1.608. So the coordinates here are 0.407, 1.608. So I go all the way up to 1.5, and so this would be like 1.525, 1.55, 1.6, And then this would be 1.625, 1.65. Yeah, because every 10 is 0.25. So this line here was 1.625. And we wanted what, 1.608? So 1.625, so it'd be just below that, right about there. The next one we're going to plot is are the coordinates 0.506, 2.065. So 0.51 would be here, 0.506 would be there, right in between those two, and we're going up to 2.06. So there's 2, that'd be 2.025. We want 2.06, so 2.025, 2.05, and we want 2.06, so this would be 2.01. .075. So in between those two. 0.506. There's 2. Right there. What's the next? 0.585. So we got 0.56, 0.57, 0.58. That'd be 0.59. So 0.585 is directly in between these two. And we're going up to 2.307. 2.25. So 2.25 plus 0.125, or it's 5 squares up. So this would be 2.375. And we're trying to plot 2.307. So this was 2.25, 2.275, 2.28. Oh wait, I'm going up by the wrong number. That's the other tricky thing. Like you got different axes on each scale and applying coordinates. You know, so that's why I'm taking. I know this is very tedious. It's like, you know, it's getting more boring. I told you this is the fun part. It's worthwhile. Like take the time up front to make sure you got good scaled axes. Be very careful in applying the data. So you didn't do all that hard work, you know, over there on the chalkboard or nothing. Trying to plot 2.307, and so it would be 2.25, 2.275, 2.28, 2.35. 2.25 plus 1.25, 2.27, 2.3, 2.325. I want 2.307. So it's just above this line right here. So it was over 0.5 in between these two, right? 0.6, 5.585. Just above that line. Moving right along here. 0.706, 2.822, 2.7. 2.875 is this line. 2.75. 2.775, 2.8, 2.825 is this line right here. So it's just beneath that one. So over here and to 0.706. That one right there. And lastly, 0.814. And we're going up to 3.258. So 3.25, 3.275. So that is just above this line. So we go all the way up. Point 4, 3.258, right there. Nice. All right, clear plastic ruler. We're going to find a best fit line here. And you see it roughly falls, you know, it definitely is a trend line, right? Like as this increased, so did that. We kind of knew that by looking at the data. We would have been, you know, suspicious of the data collection, checked our data points, you know, again, not. You wanted to represent the trend in the data with, you know, an equal number of points above and below the line. So maybe 2 points on the line. And you can see how, like, if your judgment is this and you commit to that line, but somebody else might judge it like a little bit more this way or a little bit more that way. And that's why our answers can vary. So even though, you know, let's say I assigned it, I want everybody to plot that data. I would never do that because it denies you the fun of being able to collect your own data. But if I did, our answers would still be different because everybody's going to make sort of a different judgment about their own best fit line. And because we kind of know what to expect, if we got an answer that was just a little bit off, we could have said, oh, I should have made my line a little bit steeper. I knew, you know, that was the better best fit line. Feel good about this. So that's my best fit line. Never force it through the origin. If it, doesn't seem like it's going through the origin, really just look at the data points. Now I scour the plot to try to find really good points. Like this guy right here is really good. Okay, and the reason why it's so good is because we're going to probably zoom in on it. See that it perfectly intersects the gridding of my graph, right? So I can read off what the coordinates would be. So the line, remember, is more accurate than the data points. And so we want to try to find 2 points that are on the line that are convenient to read off. Another rule of thumb is that you want, like I'm going to find the slope between this point and another point, right? So really what I'm doing is making like a triangle. You want the hypotenuse, right? So like this is the hypotenuse, you're going to construct a right triangle. You want the hypotenuse to be more than half of this line. You wouldn't want to find 2 points really close together to find the slope. Okay, so try to find 2 points that are more than half the line away from each other. So this is this rule of more than half, okay? So I want to find a point way up here if I can. Look at that guy right there. Nice. And I'm going to circle the 2 points that I'm using as my slope calculators. If I took my time to make a nice convenient scale, it should be easy enough to sort of read off, what the coordinates are. And so this one is just before this line at 0.35. Remember, each one of these went up by 0.1. So the x coordinate of this is 0.34. The y coordinate is, it's this 5 squares up from 1.25. So it'd be 1.25 plus 0.125. So this is 1.375, right? Right in between 1.25 and 1.5. So my coordinates are 0.34, 1.375. Kind of tough to read. I'll say it again in case you're note down. 0.34, 1.375. Over here, this one is the line just before 0.85, and so the x coordinate is 0.84. The y coordinate is this one between 3.25 and 3.5, so that's what, 3.375, right? 3.25 plus 0.125, yeah, 3.375, and 3. That's that one. Okay. So I have the difference in my y coordinates, 3.375 minus 1.375, over the difference in my x coordinates, 0.84 minus 0.34. That's the slope calculation. So I've got 3.375 minus 1.375 equals 2. 0.84 minus 0.34 is a half. 2 divided by a half is 4, right? So my slope is conveniently enough 4 even. Okay, I happen to just get perfectly 4. Question? Say it again. Yeah, you don't have to ask. You always have permission to go and do what you need to do. And so my final step here is to set this equal to 4 pi squared over g, right? We set this because t squared varies as 4 pi squared over g, times L. We've already taken care of the t squared and the L part of this, and now we just need to sort of finish our analysis. So I would say 4 pi squared over g equals my slope, 4. Multiply both sides by g, divide both sides by 4, and I would get g equal to, 4 pi squared over my slope, right? This is a little bit of algebra. I could cancel out the 4 here, but if you got another number, 3.75, you just multiply 4 times pi, and then divide it by that. I'm going to cancel out the 4s, and so I really deduce that g on Earth is just equal to pi squared. Delicious pi squared, which is like 9.86. I think it actually agrees with our first data point up there. Where's my pi button? So pi squared 9.869. So I've concluded that G equals 9 point, and I'm actually going to round that up to 9.9 meters per second squared are the units because the slope had units of seconds squared per meter, okay? And so G on this side of the equation has to have, this, like this side has to have the same as this side. So the units of this slope are seconds squared per meters, right? Because I rose in seconds squared and I ran in meters. And so if the units of this are seconds squared per meter, how do I cancel that out on this side, or how do I make it equal on that side? Well, 4 pi squared doesn't have any units, so it's numbers. G does have units of acceleration. So the units here would be meters per second squared in the denominator. So it's like meters per second squared. So second squared per meters equals second squared per meters. The units agree on both sides. They should. That would be my claim. I say claim, Earth's gravity field is 9.9 meters per second squared, or Earth accelerates things 9.9 meters per second every second. Evidence, see graph. Reasoning, because theory suggests t equals 2 pi times the root L over G, I can determine G by varying the length of a pendulum string, setting it in motion, measuring its period of oscillation, and plotting a graph of t squared against L. You're basically just sort of walking back through what you did. Because theory suggests this, I've leveraged that physics to my benefit to make a conclusion about the strength of the gravity field on it.